Hello everyone. For today's video, we're diving into the discussion of triangular waveform. You'll learn what it is, how it's different from square and sine waves, and why engineers love its clean, band-limited spectrum. We'll break it down with simple visuals, real-world examples, and show you how can it be visualized through the use of MATLAB coding as well as in Simulink. So whether you're a student, a hobbyist, or just curious about waveforms, get ready to sharpen your signal skills. Let's get started. Before we dive in, let's take a quick look at what this lesson has in store for us. Here's our table of contents, a roadmap of everything we'll be covering in today's video on triangular waveforms and their applications in signal processing. We'll start with a basic understanding of the triangular wave, followed by its mathematical representation so you can grasp how it's defined both visually and analytically. Then we'll explore the 6 fundamental transformations of periodic signals, essential tools for working with and manipulating waveforms. From there, we'll move into practical implementations, starting with a MATLAB GUI, followed by a Simulink model, and even a multisim simulation to show how triangular waves behave in virtual circuits. After exploring simulations, we'll demonstrate the actual hardware implementation, bridging the gap between theory and real-world application. And finally, we'll wrap everything up with a conclusion to summarize key insights and takeaways. So buckle up. This journey is packed with both theory and hands-on examples to help you truly understand triangular waveforms in action. Let's start by defining triangular waveform. A triangular wave is a continuous, piecewise, linear periodic waveform that rises and falls in a straight, linear fashion, forming a shape reminiscent of a triangle. Unlike sinusoidal waves, which are smooth and curved, triangular waves have constant slope segments. Triangular waves are commonly used in real-world applications, such as pulse width modulation, PWM, in power electronics, audio synthesis in music technology, signal testing in control systems, and waveform generation in embedded systems. Their predictable shape and harmonic content make them ideal for testing linear systems, generating smooth control signals, and producing softer tones in synthesizers. Compared to square waves, triangular waves offer advantages such as smoother transitions, reduced high-frequency harmonics, easier filtering, and simpler generation using analog or digital methods. These properties make them efficient and practical for both analog and digital signal processing tasks. Now let's move into the mathematical representation of the triangular wave using Fourier Series, a powerful tool for analyzing periodic signals in the frequency domain. On this slide, we see the 3 standard forms of Fourier series as they apply to the triangular wave. First up, we have the trigonometric form. This version expresses the triangular wave as a sum of cosine functions with decreasing amplitudes, which are inversely proportional to the square of the harmonic index. It's helpful for visualizing how harmonics shape the waveform. Next is the combined trigonometric form, which is essentially a simplified and phase-shifted version of the trigonometric form. It allows easier analysis by adjusting the phase and emphasizing symmetry in waveform construction. And finally, the exponential form. This form uses complex exponentials to express the waveform, which is especially useful in advanced signal processing and when working with phasor analysis in electrical engineering. Notice the alternating sign and squared denominator. This shows that the triangular wave has only odd harmonics, and its amplitude decays rapidly, indicating a band-limited and smooth waveform. Each of these representations gives us a different mathematical lens to understand and analyze the triangular wave, whether you're working in time, frequency, or phase. So now we're going to talk about the 6th transformation of periodic signals these contains: time reversal, time scaling, time shifting, amplitude reversal, amplitude scaling, and amplitude shifting. First, the time reversal. It involves reversing the direction of time. This means that for a periodic signal x of t, the time-reversed signal is represented as x of negative t. Essentially, the signal is flipped about the vertical axis. The second is time scaling, also known as time stretching or compression. It alters the time axis of a periodic signal. A positive scaling factor b compresses the signal if b is greater than 1, while it expands if 0 is less than b is less than 1. This changes the signal's period and frequency. For the third is time shifting. It involves delaying or advancing the signal. This operation is achieved by adding or subtracting a time shift value to the time variable of the signal function. A positive shift moves the signal to the right, delayed, while a negative shift moves it to the left, advanced. Followed by the amplitude reversal, also known as amplitude inversion, since it flips the polarity of a signal's amplitude around its zero axis. Resulting in inversion, next is the amplitude scaling, also known as gain or multiplication, since a periodic signal is multiplied by a constant factor, altering the signal's intensity or amplitude without changing its frequency. And lastly, amplitude shifting. Basically, it involves changing the amplitude peak value, making it taller or shorter by adding constant value to the signal. To visualize and further understand this concept, let's look at how we applied the 6 fundamental transformations of periodic signals to a triangular waveform using our MATLAB GUI. This graphical user interface was built using MATLAB's App Designer or Guide. It allows users to interactively generate a triangular waveform and apply various transformations to observe the effects in real time. Now I'll walk you through the MATLAB GUI I developed for generating and transforming a triangular waveform. The GUI consists of input fields for amplitude, frequency, and the number of harmonics used to build the waveform using its exponential Fourier series. When the user enters the values and clicks the Generate button, the program calculates the triangular waveform using the Fourier series expression. Below the input section, the GUI also provides controls for 6 signal transformations. You can shift the waveform in time using a time shift input. You can also scale it in time to compress or stretch the waveform. There's a checkbox to reverse the waveform in time. For amplitude, users can scale the signal up or down, shift it vertically, or reflect it about the time axis using an inversion option. All these transformations are applied through mathematical operations on the time vector and amplitude values before replotting the waveform. First transformation is time reversal. In our GUI, this is implemented as a checkbox that flips the time vector. This is useful for analyzing mirror symmetry in signals. Once the waveform is generated and transformed, it's displayed in the plot window of the GUI. The GUI also computes and displays key electrical properties like the peak voltage, the RMS value, and the DC component, which are important in power and signal applications. Next is time scaling, which compresses or stretches the waveform. A value greater than 1 compresses it in time, while a value less than 1 stretches it out. This transformation affects the frequency content of the signal and is essential in modulation and sampling analysis. Third is the time shifting. This moves the waveform left or right along the time axis. In the GUI, we can input a value to delay or advance the waveform, helping us understand signal alignment or synchronization in systems. The fourth transformation, we have vertical reflection or inversion. This flips the waveform about the horizontal axis, turning all peaks into troughs. It's especially useful in analyzing signal polarity in waveform symmetry. Followed by the amplitude scaling. This adjusts the height of the waveform by multiplying it with a constant. In our GUI, users can scale the waveform up or down to see how amplitude affects power and signal strength. Lastly, we have the amplitude shifting, which moves the entire waveform up or down vertically. This transformation is commonly used when offsetting signals for analog transmission or adjusting DC levels. In summary, the MATLAB EGUI integrates signal generation, transformation, and analysis into one interactive platform. It bridges the gap between mathematical theory and real-world signal behavior. Now we move on to the simulation of signal transformations using MATLAB Simulink. In this demonstration, we showcase 6 fundamental transformations: time reversal, time scaling, time shifting, amplitude reversal, amplitude scaling, and amplitude shifting. Each simulation visually illustrates how these operations affect the original signal, helping us better understand their impact in signal processing. To simulate the 3 time domain transformations, time reversal, time scaling, and time shifting, we first generate the original triangle wave using a MATLAB function block that implements the exponential Fourier series. In this simulation, we generated a triangle waveform using the exponential Fourier series. Let's break down the parameters used in the MATLAB function. First, A represents the amplitude of the waveform, and it's set to 1. This determines the peak height of the triangle wave. Next, N is the number of harmonics included in the series. We use 20 harmonics to create a more accurate approximation of the waveform. More harmonics mean a sharper and more defined triangle shape. The parameter F is the base frequency of the wave, set to 0.5 Hz. From this, we compute the fundamental angular frequency W0, which is 2 pi times F. Lastly, we use a for loop that sums the complex exponentials of each harmonic from -n to +n. Only odd harmonics are included, which is a key characteristic of triangle waves. Each coefficient Cn is calculated using the formula -2a over pi squared times n squared. After summing the series, we take the real part of the result to produce the final waveform. Here's the output waveform, which is the original triangular waveform. For time reversal, we modify the input to the waveform function by multiplying the time vector by -1. In Simulink, this is done using a product block that multiplies the time signal by -1 before it enters the waveform generator. This causes the waveform to reflect across the vertical axis, creating the reversed signal as seen on the scope. For time scaling, we change how time flows into the waveform generator. A gain block is used to multiply the time vector by a scaling factor. For example, if we apply a gain of 2, the signal appears stretched, evolving more slowly. If the gain is 0.5, the waveform compresses and moves faster. This simple multiplication directly scales the time axis of the signal. Lastly, for time shifting, we add or subtract a constant from the time input using a sum block. A positive value causes the waveform to delay, shifting to the right, while a negative value advances it to the left. This shift does not change the waveform shape, only its position along the time axis. In Simulink, this is implemented using a constant block connected to a sum block before feeding into the waveform generator. This slide compares the original triangle wave with 3 time domain transformations: reversal, scaling, and shifting. Time reversal flips the signal horizontally, time scaling stretches or compresses it, and time shifting moves it left or right. Each changes the signal's timing but keeps its shape intact. This is the Simulink model used to generate and transform the triangle waveform. At the top, we see the original waveform generated using the triangle wave XP function. Below it, we have 3 separate blocks performing time domain transformations. For time reversal, we multiply the time input by -1 using a gain block, which flips the waveform horizontally. In the time reversal output, the triangle waveform is flipped horizontally across the time axis. This means that what originally increased with time now decreases, and vice versa. The signal keeps the same shape and amplitude, but its direction is reversed, effectively showing the waveform as if it's being played backward in time. This part of the Simulink model demonstrates amplitude scaling. The output of the triangle waveform function is connected to a gain block. By setting the gain value, we multiply the amplitude of the waveform. For example, a gain of 2 doubles the height of the signal, while a value less than 1 would reduce it. This transforms the waveform vertically without changing its timing. In the amplitude scaling output, the triangle waveform becomes taller or shorter depending on the scaling factor. In this case, multiplying the signal by a value greater than 1 increases its height, stretching the waveform vertically. The shape and timing of the signal stay the same. Only the amplitude values are scaled. This block applies amplitude shifting by adding a constant value to the triangle waveform. In Simulink, this is done using a sum block connected to a constant input. The result shifts the entire waveform upward or downward on the amplitude axis, depending on the value. It changes the baseline of the signal, but keeps its shape and timing unchanged. The output of amplitude shifting shows the triangle waveform move vertically along the amplitude axis. If we add a positive constant, the entire waveform shifts upward. If we subtract, it shifts downward. The shape, frequency, and timing of the signal stay the same. Only its vertical position changes. In Simulink, a clock block provides the input time signal. Amplitude reversal uses a gain block with -1 to flip the signal. Amplitude scaling uses a gain block with a positive factor to change its size. Amplitude shifting adds a constant block through a sum block to move the signal up or down. Reversal flips, scaling resizes, and shifting moves the signal. Here's the output of 4 transformations. We use a signal generator set to triangle wave, connected to an oscilloscope to display the waveform. To reverse it in time, we invert the direction by feeding it through a function or system that flips the wave left to right, showing time reversal on the scope. In Electronics Workbench, we can't do true time reversal, but we can invert amplitude or delay signals. Time reversal is a theoretical concept not directly possible in real-time simulation. To make the time scaling, we set the signal generator to 3 different frequencies. First 2 kHz, then 1 kHz, and finally 0.5 kHz. At 2 kHz, the triangle wave becomes compressed, which makes it appear faster on the oscilloscope screen. At 1 kHz, the waveform shows its normal speed and shape without any compression or stretching. When set to 0.5 kHz, the wave stretches out, causing it to appear slower and wider. Adjusting the frequency like this allows us to control how the waveform is scaled in time, changing how quickly or slowly it cycles. To make time shifting, we use a resistor and capacitor connected in series to form an RC circuit. This circuit creates a time delay by charging and discharging the capacitor, which shifts the waveform in time. The amount of shifting depends on the values of the resistor and capacitor used in the circuit, allowing control over how much the signal is delayed. Now that we've covered the theory and math, let's take a look at the triangular wave in the real world through some hands-on hardware implementations. On this slide, we're demonstrating the 6 fundamental signal transformations using actual waveforms displayed on a digital oscilloscope. Each screen capture represents how a triangular waveform is affected when modified in time or amplitude. Let's start with the time transformations. On the left, we have time reversal. Notice how the triangular wave is mirrored along the vertical axis. This is achieved by reversing the time variable, effectively playing the signal backwards. In the center, we see time scaling. The waveform is compressed, meaning it oscillates faster than the original. This can be done using a function generator with variable frequency control. And on the right, we have time shifting. The waveform is moved horizontally along the time axis, either delayed or advanced, which is useful for synchronization in signal systems. Now moving on to the amplitude transformations. First is amplitude reversal. This flips the waveform over the horizontal axis, turning peaks into troughs and vice versa. It's often implemented using inverting op-amp circuits. Next, we have amplitude scaling, where the waveform's height is increased or decreased. This is typically done by adjusting the gain of an amplifier circuit. And finally, amplitude shifting. The waveform here has been vertically offset, meaning a DC bias has been added or subtracted, commonly done using a summing amplifier or by injecting a DC offset in the signal path. Now you might be wondering, What components can be used to generate and manipulate these triangular waves? For waveform generation, you can use a function generator, like the one shown here, to produce a clean triangular wave directly. An op-amp integrator circuit fed by a square wave input to create a triangular response. Microcontrollers or DACs for digital waveform synthesis, especially if you're working in embedded systems. To modify these waveforms, use operational amplifiers for inversion, gain control, and DC offset, variable resistors or capacitors for time scaling or frequency tuning, and digital signal processing if you're implementing these transformations in code. Together, these implementations bridge the gap between mathematical models and real-world applications, whether you're building filters, audio circuits, or control systems. And that brings us to the end of our lesson on triangular waves. As shown in this final slide, we've focused on how a triangular wave behaves under 6 fundamental signal transformations: time reversal, time scaling, time shifting, amplitude reversal, amplitude scaling, and amplitude shifting. Throughout this video, we've used MATLAB Simulink to simulate these transformations in both the time and amplitude domains. This allowed us to visualize how each change affects the waveform, helping us grasp not just the theory, but its real behavior in practice. To make our simulations more interactive, we also created a custom GUI in MATLAB, allowing real-time observation of signal behavior. We then took it a step further by using Electronics Workbench to model these signals in circuit form. And finally, we tested everything on actual hardware, confirming that the concepts and simulations we studied do translate into real-world applications. Key takeaways from this lesson include understanding the basic shape and properties of a triangular waveform, learning how triangular waves are represented mathematically, especially through Fourier series, observing how waveform transformations affect both time and amplitude, bridging simulation and physical implementation using MATLAB, GUI tools, and real electronic circuits. This lesson strengthened our understanding of signal processing and showed how software tools and hardware setups can work together to analyze and manipulate waveforms. Whether you're a student, an engineer, or just curious about signals, this foundational knowledge is essential for your journey in electronics and communication systems. Thank you so much for watching. If you found this video helpful, please give it a thumbs up. Don't forget to subscribe to our channel and hit that notification bell so you never miss an upload. Until next time, stay curious, keep experimenting, and keep those waveforms clean.